Okay, this is now recording, so let's start now again. So this is lecture 11. We are going to talk about modular programming in C and assembly. During the last 2 weeks, we talked about subprogram in assembly, which are the equivalent of functions in C. And we explained how we can pass arguments to these subprogram in assembly, which there are two main ways. One is using registers, and the other one using the stack. He said that registers are easier to pass the arguments, but the stack going to be very useful at the time when we don't have enough general purpose register available to us, and our program is a bit complex, and the number of argument and parameters that we have are like more than 15. So at that time, then, since we don't have enough register, then there is no way to do that except to use the stack to pass the arguments to subprogram. Last week, we also talked about ASCII code, right? So we said that when we press a key on the keyboard, the value that entered to the computer is not the character that we see on the keyboard. So once you press the keyboard, there's going to be ASCII code associated to each of these code, which is 1 byte in length, and it goes into the memory. And this is for us as an assembly program. It is up to us to decode that value and process the data after that. So, for example, when we press number 0 on keyboard, the number that enters to our program is 30 hex. And if we want to multiply two numbers like 1 and 5, the number and the code that enter to the computer is 31 and 35. So if you want to do the multiplication, then we have to do the decoding and do a multiplication afterwards. And if we want to send the result out to the screen, then we have to do the ASCII coding again for each digit. So your lab number 8 was about that, character classification. So basically, we wanted you to enter the string of data into the computer, and then in your code, you classify these characters into 3 categories of numbers, alphabet, and special characters. So based on the code associated to each of these characters, you could write a conditional statement and then put all those 3 classes in 3 different places in the memory, and then you can print it out using Linux call function, a write function. So as I said before, so in this lab, you shouldn't be using the print string or read string macros, because those macros automatically decode the character from the keyboard, and what you see is the decoded version of the character in the computer. So what you want for lab 9 is the uncoded value of that character so that we can classify that. So if you haven't done lab 9, just have this point in mind that you shouldn't be using the print and read macro that we have used before for simplicity. So you need to use Linux system call, read, and write to do that. And one thing else that I would like to mention here for this lab is that the end of the string for your character going to be specified by character 0xa. So once you write a string of data using the keyboard, right? Once you press enter, the character 0xa going to be appended to the string and going to be saved in the memory. So this is the way to understand that, okay, this is the end of your string when you're doing the processing for your string. All right, that's enough for last week. So let's start the lecture for this week. Modular programming. So this is an example about modular programming for C. And let me explain why we need modular programming before I start explaining about this simple example. All right, the reason that we actually need modular programming is because when we are writing a complex function, a complex program, it might consist of uh, many lines of code. And if you're in a company or in an organization that many employees are working on the same project, then this is not possible that we do it as a batch, in one shot. So we have to divide the project into multiple sections and then assign each section or function or sub-project to a different team. And once all those are implemented, we can put it together and run it as one whole project. So basically, this is a block diagram that we can show for a modular program in C or assembly. So here, it assumes that this is your main function. You have your main function at the top, and then you have your subprogram or function making that the whole project. So here is my function 1, function 2, and function n-1 and function n. And then we again might have like another layer of function that's kind of nested in those function and depend on the previous function. We call this one function n plus n. And then we have function n plus 2 and n plus m at this layer. So all these functions are a subset of or a part of the main function. So when the main function can act as a controller, and all these second layer function can be dependent on the layer before. And then we're going to be assuming that we have a 2-layer project that consists of this much function. So this is going to be our output, and it's going to be our input to the main program. And each of these functions also can have their own input that somehow it's going to be defined in the main function what they are. So I'm going to explain in how we can do that, so that when you define parameters in subprogram or function, how that can be defined in a main function. So assuming that you are working in an organization, some of these functions might be assigned to different groups, right? And then each individual group is able to verify the functionality and correctness of each part. And after that, it can be delivered to the project manager so that they can put it together and run it as a whole. So let me give you an example where in practice you can see it, kind of this modular programming. All right. So when I was a software engineer at Qualcomm, so we have been working on a chipset called like a modem chip. It was a big project. We're about like 27,000 people working on this project. So one of the tasks for the team, for hardware modeling team, was to come up with the golden benchmark for the whole chip, so that when they implement the hardware and they input some numbers into it and they get some output, there is a way to verify the functionality of the implemented hardware by other engineers. So the software engineer team and hardware modeling team, their task was to actually models this modem chip, and therefore, because that was a big project and was not able for one team to implement all of it, so it was divided into different modules. So I'm gonna name some of these modules for this modem chip. So was a modem subsystem or Snapdragon, and at the top we have our like main function at the top, and then we have different modules in this chipset. So one of the modules, for example, was of Wi-Fi. The other one was the cellular data, like 4G, cellular system. And the other one was the Bluetooth module. And the other one was video processing module. As you know, that these smartphones, they have good cameras and they can process images and they can process videos, right? And the other one was the image processing module. So under each of these module, you know, there were so many sub modules that each, for example, for the Wi-Fi, there was like thousands of people working on this, right? And these also divided into two sub modules and then assigned to a group of people with, for example, maximum of 40 people. And then, so each team, you know, then they test their module, the software, and they make sure that it's working properly. And then, for example, cellular system, Bluetooth, all of them, they're working on this sub-module and they make sure about the correctness of their model and they send it for integration for the modeling of the whole chip. So that's how we have been doing that in Qualcomm. So in practice, there is no way that you can just run away from the modular program. You have to do it in that way. So there are two reasons. You simplify the complex tasks into a simpler task. And the other one is that you are able to divide a complex system implementation into different group of people so that they can participate and contribute to the whole project. So this is the philosophy and reason behind the modular programming. So in this lecture, we're going to talk about modular programming for C, and modular programming for assembly, and then see how we can compile this project in an easy way using Makefile utility in Linux. All right, so let's start with this one, with this program. This is a simple program that we have. This test C is our main program here, where in test C, we call factorial function. This is a simple program that you define a number, then you call a factorial function, and then you print the result on the screen. So we have two files. And so this is one module for this project, for example. So one person work on the main function, other person work on the implementation of the factorial and some other function. So this is another function that tells how two numbers are compared with each other. So the factorial implementation is here. All right, so let's take a look at the implementation of it. So these two programs are implemented in two different files, right? And then you will see that in our function, we have some variables defined, right? And then we have a flag defined here as static, and then we use this max value in this function, and then we use value of the flag in this function, and value of n that's going to be assigned through the main function. So as you can see here, we define max value in this function as a local variable, So that's an integer function that's defined in this function. So if we want to tell the main program that we have a variable defined in some other function, and we want to use that in the main function as well, we use the keyword extern. Extern tell the program, okay, this is a variable. This has been defined in different modules or different function, but we kind of declaring that at the main program in here. So upon, when the compiler reaches to this line, it doesn't allocate any memory to this max value. It's only allocate the value when we actually define the variable in the subfunction. And also, if you take a look at this one, so normally when we are in the main function, and if the function is defined in somewhere in here, we prototype that function at the beginning of the main, right? We don't use the extern. So if the function is not defined in the main file and it's defined in the other module files, then we have to tell the compiler, okay, this is externally defined in another file, just to let you know that, so that when the compiler goes to the main function and wanna call this, then it knows that, okay, this is externally defined in some other file. I'm gonna look for it and find it, and then use it in here when I call it. So therefore, extern tells us where the function is. Implicitly for function, when we are prototyping that at the beginning of the file in C, implicitly they are extern. So you don't need to use the extern keyword at the beginning. Therefore, let me check my participant if anyone. Okay. All right. Therefore, you can see from here that in our implementation, we didn't define function as an extern because that implicitly implied. But for variables, we need to define as extern if that value is defined in some other file. All right, this is enough of this. So this is just a reminder of what we talked about during the past lectures about compiling several C files together and linking them to the linker. So if you remember that, so we use GCC to compile this test.c and create the object file. And then we use the compiler GCC to compile this and create the object file here. And then we link the library and to this object file. And at the end, we create the executable at the end. So this is just a reminder, we have done this before. So you saw this graph before. So this is how we implemented it. We see GCC minus C, test C. When we use minus C option here, we create the object file. If we don't put that, then the compiler thinks that it has to create the binary for it. And since this test.c depend on the other function and files in our project, then it's going to give you an error. So you put minus C to create your object file. So we will create in our object file here and here. We link the library to the linker in here. So these are the libraries. These are telling the linker that these are the input file. And then we put this library at the end. So basically, this is one very long syntax in Linux. And then we create our executable. So in the class, we mentioned that instead of writing all these libraries, we can ask the compiler to GCC compiler to do that for us. And we said that, okay, GCC is two object file, and then the compiler going to be producing executable for us even without mentioning the libraries. It's going to automatically take a look at this test.i1 fact and figure out what libraries are needed for it, and then link the library, and at the end create the binary file for us. Okay, that one, previous example, this example, because we didn't say anything about the length of the register or the architecture of the CPU. It's assumed that it is 64 bits. So it's going to produce for us 64 bits executable that only runs on 64-bit machine. If our intent is to generate a 32 bits executable, then we need to put this keyword in our compile to create the object file. So once you do that, then if you want to tell the linker, okay, you need to link this one for a 32-bit machine, and this is the keyword that you need to use for your linker. Again, we said that all these library can be simplified using GCC, and we can use another command like here. We say what our object files are and what's the architecture of the machine that this code is going to run. So in this case, -M32 is the GCC option that we give to our compiler to create our object file and to create our binary. So this is what we talked about before, but just we review it. And actually we use modular programming throughout this course, but we didn't know that. And in this lecture, explicitly say what this is. All right, now this comes the time for explaining the makefile. If you remember in our implementation before, to automate all these, creating the object file and running executable, we create a bash file. So .sh file in Linux, and then we just call that sh file and give the name of the output file as an argument, and that our shell script file was going to compile all those files for us and at the end run the program. Here we have another utility, makefile, that's also automate the compile and execution of modular C or assembly program for us. Here is the way that we can implement a makefile. If you remember, for our shell programming, the architecture was going from down to top. For example, we start with saying, okay, create the object file for us in the first line for this file, create the object file for us in the second line for this file, and then we said, link this together, create a .out file. So .out was created at the end of the file when we run the shell script. But here the architecture is a bit different. So the output that we want the makefile to create for us comes at the top here. And it says, okay, this is the output of this makefile that I'm going to create. So what this output file need as its argument? It needs two files, s.io and fact.o. So these are the input to the GCC comment in here. So we specified, and now we are implementing this, okay? So we are implementing this in this line. So we say that the a.out is the output of it. So what are the input to this command? It's fact.io and test.io. So the input gonna comes in here. And then we say, okay, what is the command that's gonna create a.out for us from these two inputs? So basically, it's going to be these two files gonna be selected as an input, and this is the GCC compiler command, and we say that, okay, create for us a 32-bit architecture, right? So GCC do this, these are the input, and then create the a.out for us. But how test.io and fact.io can be created? So they come next. So in here, we create test.io. Where it is come from, it was generated from test.c. And how we do it, this is the command that we use to generate it. And then we have fact dot o. What is the input to the Linux argument that we use is the fact.ic. And how we do it, this is the gcc -m32 -c fact.c. So as you can see from here, the architecture is from top down, but in shell script, the architecture was from bottom to top. That's the difference. So Linux comes here, take a look at a.out. It sees that it needs test.io and fact.io, and it sees that it doesn't have those input. And then it comes to the next line in here. It sees that okay, test.io can be created from test.c, and this is the command. So it knows that it has test.c, so it's execute this one and create test.o. And then it sees that, okay, what else he needs to run this one, it's look for fact.o. And it sees that, okay, fact.o can be created from fact.c using this Linux command. So it's run this one, and then create fact.o, and it's plugged those into this. And finally, it creates the a.out, or our binary for this simple example. Okay, so this is another, implementation for automation, automating the compile process and linking process in C and assembly. Why we are doing this is shell script not good enough for us, so that we need to go to do this using makefile. Yes, there are advantages of using makefile. Makefile actually is very useful when you have a big project like 100,000 lines of code or 1,000,000 lines of code, a project that consists of millions of lines of code. In Qualcomm, we have a project that consists of that much line of code. It was very huge. So if you're using the shell script to compile and create object file and the binary file, then the shell script gonna go line by line, execute each line, and do the compile, and at the end create the binary for you. So it doesn't care whether there is a change in that specific file. It's gonna do that, no matter what. But makefile is intelligent. Makefile, take a look at this file, the input file. If there is no changes in the input file, test.c or fact.c, it doesn't run that specific command in the makefile. For example, if there's no change in test.c, because you're going to be running and compiling this project for many, many times during the implementation. Sometimes you change some files and you run and see whether it works or not. But sometimes, you write all the functions and then you run it. For the first time, all of the functions are going to run. But for the second time, only those files that has changed in the process gonna be compiled. So the other files that haven't had any changes, they're not gonna be compiled again. So you can see this one in an example that we have in here. So we can try that in Linux to see if this actually is a case. All right. Let me open the Linux file and do some experimentation for this and see if this is actually the case. In here, in this example, you see that we say make, and it says make a.out is up to date. So it doesn't do anything, because in previous slide, in here, we didn't have any changes. And previously here, we used makefile to create these two files. And that's the reason it does it one time. And if you type make again, it is smart. It doesn't do it. It says that, okay, I compiled, I create the executable, and there is no reason for me to do it again. It's waste of time. It's gonna be just waste of resources. And you assume that if you have like 100,000 lines of code, it's gonna take like maybe up to 2 or 3 hours to compile and run again. And if someone in the group, it has a minor change in one of the file, and then this make utility is smart enough and goes only to that function and create the object file for it, and then link them together again. And after like few seconds, it's gonna give you the binary so that you can run your project, almost immediately. So let's see in Ubuntu. So anyone has any questions so far about the implementation of Makefile or modular programming? All right, so if you have any question, you can also post it in the chat, so I'll read it and answer your question. All right, let's see. Okay. So here's my program, right? So I have fact.c and so these are my input file. Modular C. Okay. All right, so let's try Makefile. It said a.out is up to date because I have compiled this before. And let's see what do we have inside of the Makefile. So this is what we have inside of the Makefile. The only difference that we have in this implementation is that we have a GCC option over here. I don't know whether I can write on it or not. So we have GCC option in here, and at the top of the file, we define GCC option as -M32. So this is a.out, these are the input to the file, and this is the Linux syntax. So once I say $GCC option, it's gonna take -M32 and put it in that file for us. And automatically create a 32-bit architecture binary file for us. And this is the test.io, use test.c and GCC option, same thing, and same thing over here. All right, let me do a bit of change in the, let me come back to the laptop mode. So that's easier to type. So let me change the test.c. Okay, we go here. Now x is 4. Now let's change x as like 3, right? Make x as 3. Then we save and come back. So now we have that file. So our expectation this time is that when we type make, it should only change the test.c. I mean, it should only compile test.c file for us, nothing else. We say make. So as you can see here, it only changes the, it's only compile test.c for us and include that object file in the process to create the executable for us. It didn't have, it didn't actually compile the fact.c because we didn't have any changes in fact.c function. So that's the beauty of it, and it's going to save a lot of time in a large project that you might see in like industry. And this is a good time for you guys to learn about Makefile, because in the company that we were working, actually, not so many people were familiar with this utility in Linux, and there was a learning curve for them to understand this. So it is good time to do some exercise and practice writing this Makefile and using it in your project. In the lab that we have, like district lab number 9, you're going to be running, writing a make file for your project that consists of like about, I guess, almost 5 files. And then you are get to have a chance to practice making file and do some changes and see how it works. All right. Let's go back to where we were before. Okay. Portion. Whiteboard. Okay, guys, do you have any question about this part, the implementation of make and how it can be done? Okay, good. Let's move on to the next one. So these are some links that you can go through for learning more material on Makefile and how they can be written and how option can be defined at the beginning and so on. But this is basically what you need in this course. Okay, modular programming in assembly. So far we explained modular programming in C, and now we're gonna be seeing how we can do it for assembly files, assembly project basically. All right, so you guys remember driver.c, myprogram.sm, and asm_.io from our lab 3, if I'm not mistaken. So we have project, so we had the mix of C and assembly file, and we wanted to create the executable at the end, right? So we said that, okay, we use GCC minus C option to create the object file for driver.o. We also have ASM file, and we're going to create the myprogram.o. But in here, we don't use GCC, we use NASM to create the object file. Here is the same, we use NASM to create the object file, and then we link the library together, and finally we create the executable at the end, right? So these are the comment that the syntax that we use to do this. Right here is NASM, here is NASM for the ASM underscore io.asm. So we create the object file for each of these. And now, since they are at the same, same type of function, we can link them together, no matter whether they come from a C function or from the assembly function. Link them together using this minus M32, and these are the input to this GCC command, and this is the option. Okay, I need the 32-bit architecture binary. Please reduce that for me. At the end, you're gonna be getting the a.out file, and you can run that a.out file to get answer for your whole project. So the point of this is that how we could, implement this in a Makefile and doing this in assembly, okay? So we're gonna be having the same example for assembly implementation in here. We start with this, and then we go back to this bigger function, okay, for a Makefile. As you remember, so we're gonna be having the same keyword, extend fact, variable, and then our code goes here for the main file. As we said, the .text gonna be where we put the main code in. So we move the variable content into EAX, we push 6 into a stack, and then we call the factorial function, and then we free the stack at the end, and then we do something else afterward, right? So now our function, when we define those variables, since it's defined as an extern in here, right? It means that, okay, these two variables are defined somewhere else in some other files in the assembly file. And the keyword to define this is like global. Okay, these are the variables that are using in here, and these variables are global and can be used in other functions. So this is the segment.data for defining a variable, initialized variable. So this is a double word, defined double word, 22 as variable 1. And this is segment.text, and your factorial code goes in here. Okay, let's go to the next one. Okay, in here, we have the implementation for this two function. Basically, we want to call factorial from here to compute the factorial of 6 for us. And the factorial is implemented in here, in this function. We're going to come back to this example and draw the stack diagram for it. Thus, just for you guys to practice more about the stack, and actually we have an example. I mean, we have our assignment, next assignment is almost about this, this code. So it's better for us to understand it in this lecture. So we're gonna come back to this example after I explain the makefile for assembly, okay? Just for this example, you know that, okay, this is the main program, in assembly program. We call function from here. We have some variable defined in different function. We have to define that as global so that it be recognized by our main assembly file in here. So that just note, take a note that the external keyword we use in our main assembly file function. Okay, so this is a function, and this is our main program. And we try to see, this is the explanation that I gave. So let's go to the next slide. So as we said in our shell file, these are the lines that we put in the script, right? So we first compile .asm to create the object file. We then compile the second file, create the object file for it, and then we have first file, we have second object file here, and so this is the output. We say that what the output is, right? This is the binary. We say -o option also always tell us what the output of that GCC command is. So this has to be GCC driver.o. You can put driver.o, but we need to create that driver.o at one line before using GCC syntax. And then also we are missing here ASM underscore IO. It should be somewhere in here. So we have to create it somewhere in here using NASM. So this is our script actually. So when we put this in the script and then we say ./first, it's gonna give us the output. Okay, here's the implementation of that compile process is in makefile. So you create the makefile using Vim. You say Vim makefile, and the page is going to be open, and then you start writing this code in your makefile. As I said, you can define at the top your option here, and once you're going to address that option in your implementation in makefile, you have to put the $sign in front of it to say that, okay, this is a variable in my code. Go and grab that content of the variable and put it in here. So once the compiler sees this one, then it's going to go and grab -m32 and put it in here. So as I said, this is a top-down architecture. So it means that the binary going to be created at the top. We say what the input to that binary is, driver.o, first.io, second.io, sm.io. Okay, and what's the command to create that first from this input? This is the command, right? Okay. Then the machine comes here and take a look at this and see, okay, it doesn't have driver.io, it doesn't have first.o, second.o, and asm.o. So it goes to the next line to find those. It comes here and finds first.o. It knows, okay, what the input's gonna be to this compile to create that. So the input gonna be yes, first.asm and asm underscore io.inc. So this is the NASM command to create that. And it does it for second.io. It does that for asm. And finally, it does that for driver.o. And once got this one, gonna be plug that into here and run this command. And at the end, gonna create the binary file of first. So once you put this in a file, then it's gonna be, the rest gonna be taken care of by Linux for you. Thus, the architecture is simple. You need to practice a bit to see, to make yourself comfortable with this kind of implementation. Any questions so far? All right. This. All right. So this is a process. You can see from here when we call makefile, right? In here, then it's actually gonna perform all those process inside and then run that. You see the command for you and create the first the binary file with the name first. So when you run it, it's gonna give you the output. This is a 22 that it grabbed from the memory, and this is the factorial of 8. That's gonna be computed for you. If I'm not mistaken, it's gonna be factorial. Okay, some practicing here. Any questions so far? I know the lecture is gonna be a bit long. Please bear with me. We're gonna be almost done with the lecture. We have to go back and take a look at the stack diagram. So I'm just gonna explain this a bit and then finish with the makefile, and we go back to the stack diagram, do some exercise together, and then lecture gonna be over. All right. I have to always make sure that we are connected. Yeah. Okay, so this is the first example that we have. There were two files, first.asm and second.asm. So we have include file at the beginning. We have segment.txt. We define global asm.main as global, and these two, a variable and function as an external. It means that these two are defined somewhere else in the project, which in our case, they have been created in second.sm file. All right, so we reach in here, we call factorial, and then we free the stack, and then finally we print the value of the 6 factorial and new line, and then we're done with the project, right? The one question in here we have is that we use print function, right? Print integer function and print NL function, but we didn't define those as external in our main function. Well, what is the reason why we didn't define those as external function? Anyone knows the answer for this?
Because we have the include at the top of the ASM file.
That's correct. Yes, exactly. Very good. Yeah. So as he mentioned, yeah, we have those two functions implemented in sm_io file, which the implementation is given in here. As you can see from here, they are defined as external. Very good. So we're now gonna come back to, so we're almost done with the makefile. The process is kind of simple if you do some exercise and get comfortable with it. We're gonna be having a lab at the end of this week. Please make sure that you go through the lab and implement it. All right. Okay. I'm gonna be switching to laptop and to tablet mode. Okay. So your assignment next week gonna be about the stack diagram and a stack frame. So how we do that for recursion function. As you know, this is a recursion function. So this is a factorial function that we implemented in here. So now we want to actually draw the stack diagram for this function and see how a stack grows and a stack shrinks after the implementation, right? So just we remember that we had our two register line. We have our ESP register and EBP register. And then we said for the stack, we assume architecture like vertical architecture like that. And we say, okay, at the beginning of the program, EBP is pointing to some stack frame that we don't know what that is, right? Somewhere in here. So we don't know what that is. We call it like unknown. Let's not call it unknown. So let's start from, okay. Start from here. Let's assume that this address is 2000 and go to this address. So anyone know what's the address for this element in the stack? This is our stack actually. What should be the address for this element in here? Don't be shy, just answer the question if you know.
When you say this, do you mean the element above the
Yes.
2000? Oh, okay.
Right.
Wouldn't that be 1996?
Exactly, 1996. So each element in the stacks consists of 4 bytes. Therefore, when we go up, the stack grows upward, but the address are decreasing, right? We explained about this during the past two lectures. And this is how the hardware architecture of x86 is. No matter if it is like 64-bit architecture, 32-bit, or 16-bit. So this is how it's done in 1976, and that's the reason they just continue that implementation. So this is our stack. So the element's gonna be created 4 by 4, 4 byte by 4 byte. So this one gonna be 1992, and this one gonna be 1988, and so on. So in your assignment, you can also start from some address, random address like this, and say, okay, this is this address. At the beginning, your EBP is pointing to some stack frame with some EBP value, which we don't know what that is. And then our ESP, we start from some address. So let's take a look at the program and see how the stack changes throughout this program, right? All right. So the first thing that we see here is our main fun. This is push A. It's gonna be somewhere here in the memory, right? When we say push A, it's gonna push the value of all general purpose register for us in the stack, and then the stack pointer gonna be pointing to somewhere in here, right? So I assume that is push the content of EAX, EBX, ECX, and so on. So the top one in here gonna be the content of the EBX, right? And it's gonna go in here. So it's gonna be all my general purpose register gonna be stored in the stack, and my EBP is somewhere in here. All right. Then we moved variable 1 into EAX. So for this program, we do two things. We just, for the sake of a actual implementation, we define a variable defined as a double word, and the value is 22. Okay, as it doesn't have anything related to the stack. Just we wanted to experiment how the external keyword works, right? So we said that, okay, variable 1 is a function, is a variable that defines somewhere in some other files in this project, and that's the reason it's external. And then move that amount into EAX and simply print that out into the screen, okay? So this is going to take this 22 that defined in this second file, put it in EAX and call the print integer macro and print L and print that value of 22. So we have that. I have shown this one, the output of this file. 22 is going to be printed. And then here is the part that we're going to be calling the factorial function to compute for us factorial of 6. Okay, so this part has actually nothing to do with the computation of factorial, as we said. This is only practice to see how the external keyword works. All right, so first thing we see here is push 6, right? So the stack pointer pointing here, and then push 6 gonna be doing two things, right? It's gonna decrease the value of the ESP pointing to this location, and then it's gonna move the contents of the 6 to the address pointed by ESP. Therefore, 6 gonna be put it in this element of the stack, okay? So 6 gonna goes there, and then we call factorial. So once we call factorial, we're gonna go over here. But before go over there, what happened to the stack? So anyone can tell me what happened to the stack at this point? This is very important, and maybe you guys know this answer for this.
Push the return address.
Exactly, that is correct. So, and what will be the return address? So we said that the return address would be, okay, when we call the function, we expect that that function gonna go do something and then come back to the next line, right? Assume that the address of this line add ESP is some value in the heap, right? And assume that, so we give it a label of L1. It's something, right? So in this example, give that value as L1. Let me just erase this. Write it again. For some reason my eraser doesn't work. Okay. I don't want to clear canvas. Okay. I want to get my eraser. Okay, get it. No, not yet. Ah.
Just try tapping on the canvas right now. No, like try erasing it. I think you do have it selected. It's just,
if I say clear canvas, it's gonna clear all this page. I don't want to do that.
No, I mean like if you just take like, do you have a stylus or something?
Oh, my battery is running low. Guys, let me to connect my cable to the computer. All right. So let's not stop here so I can write it over here. So let's assume that the address of this line is L1. Okay, so the return address that goes to the stack, so I write, okay, now it's going to delete. Oh, it doesn't work on this page, but it works on the main canvas page. Okay. Guys, it doesn't work on the PDF, it only works on the canvas. Okay, so we have 6 in here. Then the next thing gonna be saved in the stack is gonna be the return address. I don't write the complete wording, so I say read. So the value gonna be L1. This is the address of this line in the program counter in the heap. So it's gonna be read, and then the value is L1. We call it L1. So you can give it a number or whatever you prefer. Here I choose to give it L1. Okay. So we go here. So L1 gonna be stored in here, and then we have, guys, this command. Okay. What is this command? This command actually is 2 things. It's gonna push the value of EBP to the stack, and it's gonna move the value of let me just say EBP, ESP to EBP, meaning that it's gonna create the new stack frame for me starting here. So, but what it does, it's gonna move. So right now, assume that EBP is somewhere in here and its address is 1000, okay? So it push this address 1000 in here. So I say EBP, which the value is 1000. So we store this value so that once we come back from the current stack frame, we can restore this EBP to its previous address, so it can point to this place of the stack, so that we can retrieve the previous stack frame. Okay, we save the base pointer of the stack frame so that after we're done with that frame, we can retrieve the previous stack frame in the stack, which for us is this frame. This is this frame. Okay, now EBP is pushed. So as we said, enter 00, it is doing 2 things for us: push EBP and move ESP to EBP. Now ESP is actually pointing to this, right? And once we say move EBP, ESP to EBP, then our EBP gonna be pointed to the same location in the stack pointer, and that's fine. It's perfectly fine. There is nothing wrong with it. Okay. So this is enter 00, and again we have another function in here as leave that you guys didn't see before. This does the reverse actually. So it's move the value of ESP to EBP to ESP, and then it's retrieve the previous address of EBP. It does pop EBP. So this is these two are counterpart. Enter and leave are kind of counterpart. So we explained about this. We said this is happened to any subprograms that we implement in assembly. We said that this is one of the ABI rules to actually update your base pointer, your stack base pointer, when you enter the function, and retrieve the base pointer when you exit from it, okay? So that's the reason to simplify these 2 commands in the subprogram, they use enter 00. Let's, at this point, not to worry about this argument 00. This is actually for the nested function, and 0 means the number of the local variable you want to allocate for this new frame. So for now, I say 00, and then you don't worry about this 00 at this point, okay? We don't have any implementation that we want to allocate some local variables. So, all right, guys? So just know that the inter gonna do these two things for us. Okay, so now we're here, right? So we said that, okay, push EBP, which is 1000, and then we said that, okay, EBP and ESP point, move ESP to EBP. Therefore, now they point at these two similar location. Now let's move on to see what else we need to do here. In here, we have a move command. They say move EBP plus 8 to EAX. So what is EBP plus 8, guys? Now my EBP is point. At this point, it's pointing to this location, 1988, right? If we say EBP plus 4, it's going to point to 1992. If we say EBP plus 8, it's going to be pointing to 1996, right? Therefore, this syntax in here going to be moving the content of this element from the stack and put it in EAX register. Okay? As simple as that. So then what it does, it compares EAX with 0. If it is greater than 0, it goes to the recursion. Okay? So now my EAX value is 6, is greater than 0. Therefore, we go to recursion. In recursion, we decrement the value of EAX. So let me write something like this. We say EAX. So now the value is 6. We decrement that, the value now is 5. Okay? We decrement that, and then we push it into the stack. Now we push the value of 5 into the stack in here. Okay? Now is the recursion function, right? We then again call fact. So once we call this factorial function, right, we're gonna be directing to this location again, right? So what happened to the stack at this point? Anyone knows the answer? Don't be shy. The wrong answer is appreciated as well. Don't worry about that. You have the same assignment, guys. Remember that you want to do. So just if you want to make a mistake now.
It pushes the return address.
Okay, what's going to be the return address at this point?
Oh, it's the address for the line of the call fact within the recursion subprogram.
Okay, it's going to be this line, right? We call it L2, okay, right?
Yeah.
So we expect that when the call fact finishes, it's going to come back to the next line of the code, which is, we call it L2, right? Therefore, we put here as a return address, and we call it L2, right? Okay, we call it L2, and then we go at the top again, right? When we go at the top, it is inter 00 is the same thing. It's going to be pushing EBP value and move ESP to EBP. Therefore, our EBP at this point, right, is pointing to this element in the memory, right? And that value is this 1988, right? So we say EBP value with 1988. So it pushes that, and then therefore the stack pointer right now, always remember that the stack pointer moves as your stack grows, right? So we are in here, and then we say move the ESP to EBP. Therefore, your stack, your EBP value, the current EBP value gonna be this location in the memory. If it is 1988, this one gonna be 1984, and this gonna be 1980, and this gonna be 1976. These are the address of the stack at the right side. Okay, now we have EBP 1988, and then we say, okay, move EBP plus 8 to EAX. So what is the value of EBP plus 8 what is the bracket EBP plus 8?
Five.
It's, can you repeat again?
The value would be 5, but its location would be 1984.
Exactly. So we put the content of this address into EAX, which is 5. That's exactly correct. Therefore, we put that into EAX, and then we compare EAX with 0. It is 5 right now, right? Since it's greater than 0, we jump to the recursion. So recursion is here. What we do, we decrement the value of EAX. Now EAX become 4, right? And then we push the EAX value to the stack, right? We push it in here. Therefore, the stack pointer now point at this point, while EBP is at this point. Okay, and then we again call fact function, right? And once we call fact function, what's gonna happen? You're gonna be storing the return address, right? What is the value of the return address? So we are at this point, right? The return address is the next line in the code, which is L2. Okay. So guys, this process continues until we reaches to this one, right? So we're gonna have a stack, repeated like that, until when? Until we reach the value of EAX to 0, right? So now EAX is at the point that EAX is 0, and we are at this point. Assume that we reach at this point. Okay, now it says comp EAX with 0. If greater, go to recursion. But this time EAX is 0. It's not greater, so we go to this line, right? We go to this line. We have depopulate EAX with 1. So this is my EAX value. Now EAX get the value of 1 in here. If you learn this example, then you're gonna be fine with any recursion function, right, guys? Just understand this, how the process works, and that's you're gonna be fine. So once we did that, we jump to the end fact. Okay, this is end fact. We come to the end fact. In end fact, what we do, the first thing that we do is leave. It actually move EBP to ESP and pop EBP, right? Okay, so we are at this point. So the address might be something like 90, 50 or something. Assume some number. I don't know exactly what the value of the stack gonna be. All right. So we push that value into EAX, and that value is 0. And now is that, and then we jump to the end function, end factorial, and end factorial take us to this. We move EDP to ESP. At that point, we need to know what the value of EDP is, because okay. So EBP gonna be some value below. Okay, it's gonna be this value. So this is gonna be our EBP value, and EBP value is the address of the previous stack frame. Return value L2. Okay, guys, I guess we have to go through the stack all the way up. It's so that we know what the value of EBP is exactly. So here we didn't have enough space to do that. One thing we can do is reduce the number so that we can try it for example, number 3 or number 4. so that we know exactly what the value of EBP is. So that we can come back to the EBP and ESP, and then go to the return value. Okay, assuming that EBP is here, we put EBP to ESP, and then we put the value of the previous value of EBP to the stack. It's going to be related to the value of number 1, right? Since we haven't run it until 0 and we stop at number 4, we don't know that value, guys. All right, what I suggest is that instead of going from number 6, right, we start by implementing that from number 3 so that we can come back. Or if you have like enough space on the paper, you can try it and go for number 6, right? Now, if we assume that we did this for number 3, right? So this number, it doesn't change anything. It just changed the value of the number that we store in the stack. So because of the space limitation, we put 3 here. The next one, we change to 2, right? And the next one is 1. Okay, let's do it with this color, 1. Okay, so we call it 1. And at this point, we decrement it. And we go in here, we compare with EAX. The value is 1, it's still greater. So we go to recursion, we decrement EAX. So our value changes is in here 3, 2, 1. And we decrement EAX, should this become 0. We decrement EAX 0 and then push this 0 into memory. So this is 1, this is the return address L2. The return address, okay. Now we are at this point, push that into EAX, and then we call fact2. Then we put the address of L2 in here. And then we call the factorial again. We go at the top. And then again, we're gonna be storing the value of EBP. For this case, let me erase this. Okay, we're gonna be having the value of EBP this time. We're storing here. Because of this line, we push EBP. The value of EBP at this point is 1976. 1976, that's we done. And then we say move. Now our ESP point at this point, right? And therefore, in the next line, we say ESP move to EBP. And now the stack pointer, the base pointer also point at this point. So if this is 1976, it's going to be 1972. It's going to be 1968. And the address of this location is going to be 1964. Okay, it's going to be 1964. And then the next address is going to be 1960. Okay. So now EBP is in here. We do that, right? Then we move EBP plus 8 to EAX. This is our EBP plus 8 going to be 1. 1 going to go to EAX. And then it's again greater than 0. Unfortunately, we have to do one more time. So we come to the recursion, we decrement EAX. Now it's going to be 0. And then we push that 0 in here. And then again, we call the factorial. We have the return address at this point. The address return is again L2. And then we go to the enter 0, 0. We push EBP again in here. EBP, and the value of EBP is 1964. Okay. And then so that ESP is pointing at this point, and then we say, okay, ESP goes to EBP, therefore our EBP also point to this location at the top. All right, so now we are here, and then we say EBP plus 8, move it to EAX, compare with 0. Now it's 0, so we compare with 0. If it is greater, it's not greater, therefore move EAX value of 1. So now we're here. We say EAX become 1. Now we move EAX 1, and we say go to n factorial. N factorial, we have two functions, leave, where in leave, we move EBP to ESP. So at this point, EBP is 1964, and it's going to be moved to ESP. These are the same. Therefore, ESP is again 1964, and we pop the value of EBP, the value at the top to EBP. So therefore, it's going to be 1964, and then we have the return function. The return gonna take us the value of the next element into the program counter, and it's gonna send us to that location in the heap. So in here, if you look at that, return is L2. So we're gonna go to L2 location at this point. So when we go to the L2 location at this point, then this address, so it's gonna be crossed off automatically by return, and then we have add ESP plus 4. So ESP gonna be pointing at this point now. So now when we say ESP plus 4, we basically destroy this location in the stack, and then ESP is going to point to this location. Then gonna be add ESP plus 4, but what we do next is I multiplication, the double word EBP plus 8. Now, you said that EBP is at this point, right? Then EBP plus 8 gonna be this one. Therefore, what it does for us is 1 multiplied by 1. It's gonna do 1 multiplied by 1, and it's gonna put that into EAX register. So EAX now contains 1 by 1. And our EBP is at this point, right? Okay. So now we do that, then we automatically go to end fact location because there's no other jump or anything in here that put us back in somewhere else, right? When we go to end fact, then we see again leave function. Leave function gonna be moving EBP to ESP value and pop the EBP value to our function. So then for this one, EBP gonna be restored as this one. EBP gonna be 9088, right? Now the address of EBP gonna be 9098, and then we're gonna be returning to the next function. So when you see return, since we push this back, the next line, next element in the stack gonna be our return address. So as you can see here, return is L2, and we again go to this location in the stack. So now is L2, at L2 is add ESP plus 4, and therefore that location gonna go away. So ESP plus 4 gonna be going away, this one. And what we do afterward is I multiplication. I multiplication, EAX now has the value of 1, but it's gonna be the value of EBP plus 8, which is 2 for us at this point. So it's gonna be multiplied 1 by 2, and then go to the next one. In fact, then we're gonna have leave factorial, then EBP gonna be going to ESP, then EBP gonna be fill up with the next EBP value, which is 1000. And then again, you're gonna be going to L2. This time L2, the value is in here. Then you multiply the value of EBP plus 8, which is 3, by your function. So going to be 1 by 2 by 3. This time, the value of EAX is going to be 6. EAX at this point is 6. All right, EAX at this point is 6. Right, so EBP is 1000, EBP EAX gonna multiply by 3, it's 6. And then we go to leave function, then we move EBP, which is this address, to ESP, and pop the EBP value, which is the address 1000 here, to EBP. Means that EBP gonna go to the base frame that it was before, and then we're gonna be going to the next line, which is the return address. Now the return address is L1. Therefore, at this point, our program gonna go to this line, which is L1. It's gonna add ESP plus 1, and it's gonna destroy the value of 3 for us. And then what we left with is the previous value of EBX stored at this point, right? So it calls that, so it destroyed these 3 values, and now we have EBX. At this point, call print integer, gonna print us the value of 6, which is the factorial of 3. Goes to the next line, gonna do the pop A. We say that pop A, with push A, we put all those general purpose register into a stack. With pop A, we retrieve all those back, right? General purpose GP register gonna come back while we are in the main function. So assuming that you have another function, then you will ensure that all those register values are kind of restored for you, and can continue and implement another function in your main program.